Hey everyone, welcome to AP Stats on March 11th. Today, I would like to talk about the first part of our new unit, which is the, it's two sample inference. So we're going to start with two samples where we find a proportion from each sample and we find the difference between those proportions. Now, the purpose of this is to identify if there is a difference between two independent populations. So, to give you an example, there's been a lot of talk lately about who is receiving the vaccine. And particularly, they've been looking at the breakdown by race because they've noticed that there seems to be this discrepancy between the proportion of people who are white that are receiving the vaccine versus people who are not white that are receiving the vaccine, and hoping to make those a little bit more equitable and accessible vaccinations for everyone. So I pulled this story from Minnesota. It was one place where they've actually published the separation, the breakout between races. There's the link if you want to go observe the article, read the article, you could see this is where I got it from. So this is mostly recent. March 5th is when it was published. But at any rate, we can see that these are the proportions of people who are 65 or older within each of these races who have received the vaccine. And I think this is just at least the first vaccine. Might have to look at that. But at any rate, this is the data we can use for today. So we want to compare, how does the proportion of people who are white compare to these other races? So let's just, for today, we just want to compare two different proportions. It'd be cool to put all this together, but we don't know these population sizes. So it's hard to know what the white compared to non-white difference is. So we'll compare white, and let's just compare white to black. Okay, so suppose we didn't have this data and we wanted to estimate it. What we would do is we would take a random sample of people who are 65 or older who are white and find the proportion of them who have received their vaccine, take another sample of people who are 65 or older who are black, find the proportion of them who have received the vaccine. Then we would compare those two proportions, and we would have to do some inference because we don't know this information about the population. Some other things to note. This says only about 83% of people who have received their vaccine have given their race. And that's actually much higher than the national proportion. For the United States, it's barely over 50% who have reported their race. So this data isn't as easily attainable as you would think. So Minnesota is doing a pretty good job to be able to find those discrepancies and hopefully help out with that. So here would be a situation. We want to compare people who are 65 or older who are black with those who are 65 or older who are white in Minnesota, since we know the population parameters there. So we take a simple random sample of 50 people in the white category, and just to show you that you do not have to take samples of the same size, we will take 40 people who are black and 65 or older. In each of those groups, we will count the proportion of people who have received the vaccine. So we're going to say p-hat1 will be the proportion of white Minnesotans who are 65 or older who have received the vaccine, and p-hat2 can be the proportion of black Minnesotans 65 or older who have received the vaccine. Therefore, the difference in those two proportions is going to be p-hat1 minus p-hat2. Now we know that when we take this sample and that sample, this will not be exactly 45%, and p-hat2 will not be exactly 38.3%. However, they'll be around there, and so we're going to get differences that differ from the truth, just based on variability within sampling. So let's talk about the different types of samples that we might get. So to do that, first we should discuss what does the shape, center, and spread look like for the sampling distributions of each of these sampling distributions separately, and then we'll talk about what happens when we combine two sampling distributions, or two random variables essentially. Okay, so if you remember sampling distributions, that was the Reese's Pieces applet that showed us that. So we could simulate this. So let's say the truth was 0.45 for 65 or older that are white who have the vaccine. And let's say we sampled, what did I say, 50? And so we take a sample, and orange would be success. So those people have received the vaccine. The other colors are have not received the vaccine. So just within this one sample, we get a proportion of 0.4344, 22 out of 50. And we could do this, 100 times if we want. And we start to see the shape of this distribution. It should be pretty close to approximately normal, and we know that because of the large counts condition. So the shape of p-hat1, since p1 is 0.45 and n was 50, then we know that n times p and n times p1 minus p are 45% of 50, so 22 and a half, and then the rest, so 27 and a half, are both at least 10. So this shape is approximately normal. Okay, now these are notes, so write these down as I write them down. If I go too fast, feel free to pause the video. If I go too slow, speed it up. That's the nice thing of watching a video. Okay, the center of this sampling distribution we know is going to be at the truth. So in this case, it's going to be at 0.45. That's what the population proportion is. If we go back here. So that's easy enough. Okay. And then the spread, which is we will measure the spread by the standard deviation. That is the square root p1, 1 minus p1 divided by n. We've already derived these, so feel free to look back at your notes if you're confused as to where this is coming from. This should seem very familiar. Okay, let's actually call this M1 because that is different from the sample size that we will get in our second sampling distribution. Okay, so for the second sampling distribution, same thing, except now the true proportion P is at 0.383. And we are taking a sample of size 40. Okay, so do we meet large counts condition in this case? We certainly do. We get 15.32 and 24.68. Both of these are at least 10, so by large counts condition, we know that the shape of this sampling distribution will also be approximately normal. Perfect. Cool. And that's our hope, because that's how we calculate p-values and things like that, is with this shape that is approximately normal. So the center then is going to be at the center, the true center, or the true proportion, I guess, which is 0.383 in this case. And the standard deviation we get from this formula. Okay, I've calculated these two standard deviations. We should write these down because we'll use these here in a second. So this standard deviation is approximately 0.0704. Of course, feel free to check my calculation. If it's wrong, just write whatever the correct one is. And we will discuss later if it's wrong. Okay, so there's that. Take a screenshot if you need to. And we will move on shortly. Pause the video. There is the sampling distributions of those separately. None of that's new. We already know that. So I'm going to move on. Okay. Next, what if we want to discuss the sampling distribution of the difference in proportions? So now we're actually going back to random variables where we say we have random variable 1 and we have random variable 2, and we're going to pull randomly from the first variable, and we will pull another value randomly from the second variable, and then we will subtract these two variables. Okay, the shape of this new random variable will be approximately normal if the shape of the two random variables separately are approximately normal. So this shape is approximately normal because the sampling distributions of P1 and P2 are also approximately normal. Okay, the center. Now, I don't know if you remember this, but if you subtract two random variables, then to find the mean, you subtract the two means of the two random variables. So the center of p-hat1 minus p-hat2, or the mean of this sampling distribution, is the difference of the means, which in the case of the vaccinations would be at 0.45 minus 0.383. which is, let's find out, 0.067. Okay. So that's pretty easy. That's intuitive. That's what you would think. We're subtracting two distributions, so we would subtract the two means of the distributions separately. Now the spread is the part where you have to remember something, because this one's not intuitive. And so I don't know if you remember this, but when you subtract two random variables, it actually increases the variability that you might get within the differences. And that new standard deviation is found by knowing that the variance of the differences in proportions is the variances added. I don't know if you remember that. When you subtract two random variables, you add the variances. Variability is going to increase. There's many more different possibilities. Okay, so what that means in our case, in our example, is that well, let's keep going with this actually. The standard deviation then is the square root of the sum of the variances. And if we were to write this out even bigger and put in those formulas for p-hat, the standard deviation of p-hat1 and 2, for those variances, we would get what is on our formula sheet, which is p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. So you might want to write that down. This is on the formula sheet, though. Okay. If we plug in our values from our example, we get 0.45 times 0.55 divided by 50 plus 0.383 times, what's 1 minus 0.383? Let's see, 0.617 divided by 40. And my calculator is showing 0.1042. Okay. Too far with that one. All right. So feel free to pause the video, finish writing all this stuff down in your notes, take a screenshot if you need to. But that is it for today. We are just exploring and looking at the sampling distribution of the difference between two proportions. Tomorrow we will use this information to be able to construct confidence intervals. And then on Monday, guess what we're doing? We will be doing significance tests. Yay! Let me know if you have questions, guys. I hope the rest of your day goes well. There you go. There you go.